So I'm Bill Benn, and I'm going to talk to you about implementing extensible data structures in in-memory data grids. And we saw the taxonomy in the previous talk for in-memory data grids and data fabrics. So I think of in-memory data grids as somewhere between the previous speaker's definition of grid and fabric, but I'm not sure that will be material for this talk. So you know this is the in-memory computing conference, and really what the subject of my talk is to help you to understand how we can do more computing in memory using in-memory data grids. And we're first going to look at how in-memory data grids have traditionally been used, what are their typical access methods, both for accessing objects and for doing parallel query. And we'll look at some of the shortcomings of that, and then look at how one can move data structures into the grid and then invoke operations on data structures in the grid. And we'll look at how to make that extensible and how to avoid some of the problems of just implementing those inside of a grid service. And then last, we'll look at data parallel programming and see how that can be implemented using data structures built into the grid. So I'm Bill Benn. I'm from Scale-Out Software. I founded the company in 2003. But as I was listening to the previous talk, I was thinking I've actually been in in-memory computing since 1985. I worked at Intel Supercomputer Systems, and we built parallel supercomputers, which are really identical to today's in-memory data grids in many ways, with the key difference being that we didn't use commodity hardware. But we recognized many things. We learned a lot of lessons in those days, some of which I will tell you in this talk. And I think that it's important to always look back at the history of parallel computing when building in-memory computing systems today, because they're important lessons to be learned and help us to move forward with high scalability in these systems. So our company builds in-memory data grids, software middleware. We started out scaling application performance for applications like web server farms, using this technology primarily as distributed caching, and we quickly moved into in-memory computing to provide what we call operational intelligence, which is the ability to track the state of a live system and provide immediate feedback, sub-second feedback to a live system, and add more value to that system, give businesses a competitive edge. And there's a short talk tomorrow by my colleague Chris Villinger who will talk about some of the applications of operational intelligence. So first, let's talk about why we need grid-based data structures and what those are. So this is a depiction of an in-memory data grid. At the top, the logical view. At the bottom is the physical view. So an in-memory data grid is typically designed to host business logic state. That is to say, application state as opposed to passive state that's held on disk. So we looked at NoSQL stores in the previous talk, but now we're talking about business logic state. And so it typically takes an object-oriented view of data and hosts the data as collections of objects of a given type. So you might have a products collection, you might have a customers collection, and these are analogous to tables in a database, but they have an object-oriented view because that makes them easily accessible by Java, C#, C++, REST APIs to applications. Now, the job of an in-memory data grid for data storage is to map those objects to a cluster of commodity servers and to solve two main problems. One is how to distribute the data so that we have scalable access without bottlenecks, and also how to provide high availability so that if a server fails or a NIC fails, that you don't lose data. And then we could talk about various consistency models. The technologies we've developed follow a sequential consistency model and not eventual consistency, because the more you get to transactional data for which you can never serve stale results, then you'd want to have a sequential consistency model, the CAP theorem notwithstanding. So I put this slide in because when people look at in-memory data grids, they think, oh, in-memory computing, Spark does in-memory computing, therefore in-memory computing equals Spark. But in fact, it doesn't, and these are some interesting differences between the Spark approach and the in-memory data grid approach. The main difference is, even though they're both designed for in-memory computing and often data parallel computing, in-memory data grids host collections of individual objects which can be accessed with APIs, create, read, update, delete. We call them CRUD APIs. And in addition, they can support data structures in the grid, which we'll look at, and data parallel operators. Now, in contrast, Spark is designed to support data parallel analytics with data parallel operators on opaque, resilient distributed data sets, RDDs. So it's really solving the problem of how do you accelerate analytics in the data warehouse, not how do you provide operational intelligence to live systems. So as a result, it's not as well suited for updating individual data items. And also, it has a different availability model called lineage. We won't talk about that today. But lineage makes this trade-off that I really want the computation to go as fast as possible while providing a means for which we can recover if there's a failure. Whereas in-memory data grids have always been deployed in mission-critical systems. And as a result, they employ data replication so that you can immediately recover and provide nonstop processing to a mission-critical system, such as a web farm or maybe a medical system or Internet of Things, as we saw before in the keynote this morning. So this is just a rehash of the basic model. Notice that in-memory data grids are a key value store. So the primary access model is create, read, update, delete on objects which are typically serialized blobs of Java or C# or C++ objects. However, as we've moved forward in time, grids are now incorporating data structures in the grid, so that instead of being serialized objects, it can actually be grid-aware data structures, which we'll look at in just a minute. And that allows us to have the power of moving the computation into the grid itself. So these are a couple of examples. In the interest of time, since I have to cut this down a little bit, I'm going to just sort of skip over these pretty fast. But this just gives you a feeling for how in Java you would access the grid using these create, read, update, delete APIs. The key thing to observe there is, here, I'll turn on a little laser. What do you know? Is that you can talk about a helper object which gives you access to a collection of objects of a given type in the grid, and then perform operations by making use of this helper object. For example, here to put an object into that collection in the grid. So that's the basic access model. For those of you who are interested, here's the C# version. And notice that we've overloaded the indexer notation in C# so that a grid collection now looks very much like a pure in-memory collection. In fact, it's virtually indistinguishable. And that is very useful and syntax for applications. Now, here's another thing you can do with the basic access model is you can access remote grids over the WAN and make them all look like one virtual in-memory data grid. So there's a lot of power with these CRUD APIs. You also can do data parallel query. So instead of just looking at accessing one object at a time, you can talk about accessing groups of objects, generally out of a given collection, based on their object-oriented properties. And this is all very good, and in fact, many of our customers who come to us, the first thing they want to do is query. And I'm going to give you an example in just a minute of why query can cause problems. But conceptually, let's think about what's wrong with query. And what's motivating, why am I telling you this? I'm telling you this because it motivates why we want to move computation into the grid. Okay? So when you look at query, it's an order in operation. It's going to look at all the partitions of a collection that are spread across an entire grid. So if you have in-grid servers, it's going to do an order-in lookup, even though it might be an index lookup on each server, which it typically is. It's still going to be an order-in operation. Now, you may have in-application servers, typically the number of application servers, and we saw that slide for in-memory data grids in the previous talk, the application server farm accessing the grid farm. So you may typically have in-application servers doing queries at the same time. So now what do you have is order in squared overhead. And where does that overhead go? It goes to the network. And so the network gets quickly saturated. By the way, this is one of the first lessons we learned building parallel supercomputers is the network is the bottleneck. And I haven't heard much of that yet this morning, but the network is the bottleneck to building these billion transactions per second. That's where we have to improve the hardware component of our overall in-memory computing technology if we're going to see real scalability. But the way we can mitigate network overhead is move computation into the grid and avoid data motion, and in particular, parallel query data motion. So this is just a quick example of what does a parallel query look like, what could it look like. And in our particular implementation, we attribute properties, object-oriented properties. This is a Java example, so that you could do a query by combining query filters to query a namespace in the grid. Now here's a C# version. What's interesting about this is it employs Link, Microsoft Link, so it's got a nice, pretty syntax again for doing the same thing that we just saw. I realize I'm just throwing these slides up, but if you're interested, I'll be happy to send you the slide deck. But I'm guessing you'd rather have lunch than look at this code. So, OK, so what are we doing here? We're querying or reading the grid in order to do what? Computation in the client, the application server. So if you see here, the client is going to read an object from the grid and then perform some operation, which I'll just call eval here. The parallelogram will mean code. And then it might update the grid after it's done. So what we have here is a lot of data motion, especially if there's a parallel query. Now this is a real example with a real customer we have, which I will not name, but they they have perishable goods, and they have huge volume. They have 50,000 SKUs, and they have to be able to fulfill orders for perishable goods over the web. And so they have a stream of orders coming in, and then it turns out because these goods are perishable and are sourced from many places, then they have many inventory changes that come in. And the interesting thing is they have a highly proprietary and very cool reconciliation algorithm. So for a given SKU, they can look at the inventory and the orders and decide what orders are not going to get fulfilled. Their business challenge is that if they don't fulfill an order, then they have to give a credit. They lose money. Now, it turns out it was taking them overnight to do this, so they said, oh, we'll get an in-memory data grid and solve this problem. So they created two namespaces, one for orders and one for inventory. And then they created a set of application servers, not shown here, just as you saw in the previous talk's slide. So they had approximately 10 or 12 application servers and 10 or 12 servers in the grid, and they would dole out the SKUs, the 50,000 SKUs, to these application servers, and each application server would then, for its SKUs, do this for each. It would do first a query of all of the orders, query of the stock, and then do its reconciliation. So what does that lead to? It leads to the order in squared overhead, and therefore it didn't work very well. And it was completely saturating the network. So the solution, by the way, which is not the topic, but you might find it interesting, because it took me 2 hours sitting there listening to think of it, which is to first pre-join orders and inventory into SKU objects so that the SKU objects already, as the orders come in the inventory, instead of updating separate namespaces, create a namespace of SKUs, and then code to join on the fly the orders in the inventory, and then move the computation into the grid and run the reconciliation on all the SKUs in parallel. Now, we've eliminated data motion in and out of the grid, and we've been able to provide speed up, a very fast speed up. So going from overnight, it went down to under 2 minutes. And actually, with the final optimization of actually moving the code into the grid, it's down to a few seconds. So this is the problem. This is the problem that we first recognized many years ago, and the problem we see a lot, which is network saturation. This is a different example. It's stock backtesting. It's an example we did several years ago, but it illustrates the same thing. Is that if you can do a computation in the grid, and we just call it PMI here, I'll discuss that later, then you can get nice linear speed up. However, if you just randomly pull data out of the grid into a set of application servers, then this can kill the scalable speed up because of the network. This is all due to network overhead. So that's the problem we want to solve by moving data structures into the grid. So let's talk about how to do that. So the first step is that we think about running a method in the grid itself. So that method now no longer runs in the client, it runs in the grid. And by doing that, we can reduce the data motion because a big object doesn't have to be pulled out to be iteratively updated and then pushed back into the grid. Instead, we can just move a small parameter and a notification of which method to run, and then let it all run inside what I'll call here the grid service, because I'll use another term in a minute to talk about running outside of the grid service process. And so now we can have a very nice, powerful way to move computation into the grid, and this is the first step in in-memory computing that we can achieve. Now, what's really important here is that this technique gives rise to a grid becoming a data structure store, and of course we know that Redis has really pioneered this use of an in-memory data grid and provided a big leap in the usage model by changing the APIs from CRUD APIs to operators on built-in data structures such as lists, hash sets, sorted sets, and things like that. So the advantage of this is not only do we not have data motion, we don't have deserialization because the grid is just holding the data structure deserialized. Also, it simplifies the programming model because now the client has access to these new primitives that weren't available before. So this is an example of a Redis data structure, a Redis list. It's just a double-ended queue that you can push and pop from both ends. These are the actual Redis operators, and don't ask me what every single one is. But it's very useful for doing things like pulling stuff off of one queue and putting it on another, so you can manage messages very nicely with this built-in data structure. And so the real lesson here is that by building these APIs from the client, that are called from the client, now then you can avoid reading and updating the entire list just to append one item or to pull one item off. In addition, Redis has provided extensibility so that in the server you can run Lua scripts. And this is an example of one in red here inside of a Python program. And these Lewis scripts then run atomically, and that way you can avoid multiple round trips to the server to do an operation. So once a Lewis script starts running, it runs it completely until it finishes. And it is allowed to call the Redis commands, like calling get here, so it can go fetch data from the local server. So its visibility is the local server. And so you can see here how you can register the script and then execute the script here. This comes right off the web, so you could find that example very easily. Now, what's interesting is just this week, in fact, just Thursday, I had to modify the slide when I discovered that Redis is going to be offering loadable modules. So they've taken extensibility a big step forward beyond Lewis scripting, and so I know you want to read about that. So what are the pros and cons of this technique of running data structures, building them in the server, and running scripts in the server? Well, you get this really nice performance boost because you're avoiding data motion. And one of the problems that you have, of course, is that you can't run a language that's not supported by the server. So Lewis scripts are perfect, but say Java, running a Java program inside of the server would be difficult to do. It also has the problem of security, that you might have a script that, first of all, it might run too long and create a hotspot and cause the grid to become non-performing. And also, a script could access other parts of the grid and perhaps compromise data. And lastly, of course, it could crash the grid service altogether. So what do you do about that? Well, one thing you can do about it is run outside of the grid servers in what we call a worker process. And that creates a new set of trade-offs. It's not a panacea. It creates the benefits of overcoming some of these drawbacks, but it creates more complexity and more overhead within a server. So let's talk about how you would do that. So first thing you do is you create a worker process for each grid server. So here's a host or a server in the grid. There's, say, 3 here. And so there's the grid service we saw before where you might run data structures and implement them. But in addition, you could spawn a worker process on each grid server. And we call this set of worker processes an invocation grid. And so a request could come in and be forwarded to the grid to the worker process and execute a method on behalf of a client. So this is how that would take place. Just as before, the client invokes a method, but now the grid service forwards it to the grid worker. And one of the nice things about this is you can run your favorite language runtime. This could be a JVM, or it could be a .NET runtime, or it could be an unmanaged runtime running C++ programs. And now you can build your favorite data structure that is interpreted by this worker so that it can now also access the entire distributed grid and not just the local server process, as we saw with the original Redis scripts. Now, one of the drawbacks of this, of course, is once this operation is invoked in the grid worker, then the worker has to read the object. So an object has to either go from process to process within the server, or you can use memory map files to mitigate that. And furthermore, you can use client-side caching to avoid data motion altogether if the object wasn't updated on a previous call. So this is how you would run outside the grid service in a worker process. Now, this is an example of this that we have in our product. We call it single method invocation. And it's an object-oriented formulation of calling a method, or a data structure method, in a worker process. So the way it works is, again, we assume that the grid hosts collections of objects of a given type. And I'm not sure this was new, so I'm going to get a different one here. OK, that's better. Although it's dripping. Hang on. And so what you want to do is invoke a method on an instance of an object of that type. So we're taking advantage of the type structure built into the language like Java or C# to invoke a method remotely on an object which is an instance of that class and being hosted in the grid. And you can see at the bottom that you can encapsulate this call within a client-based API, so it looks like a Redis operator and becomes completely transparent to the user that it's a remote invocation. Now, this is the Redis list represented as a C# object. I put this up here just to show you that, yes, in fact, you could do Redis lists as C# objects, believe it or not. And it's just a subclass of the linked list built into .NET. And so we build these methods which we're going to invoke remotely. And this shows you how that invocation was done. This is pseudocode here, but in this next example, this will be real code very close to the actual implementation with some stuff left out. This is a Java example. So what we see here is a general purpose data structure with the linked list. But now you think, well, gee, I can now implement stuff. I'm using the extensibility to implement something that's application specific, but still very interesting. And this would be, to say, to do stock backtesting. So we would put in an object in the grid a collection of stock price data, so stock prices and PE ratios and dates and other information. And now we can run an operator, which is shown here, this eval operator, which is going to take that object and do some analysis on it and return a result. Now, we don't really have to care here, but our implementation pushes that method out by making it's an implementation of an interface we define in our APIs, but I don't think we have to care about that here today. The point is that the bottom line is you can now call this method on this object in the grid, on a specific object, and this is an application-specific use of built-in data structures in the grid. We originally did this, by the way, for a financial services company that was doing columnar analysis, and they wanted a way to do very efficient access to a column and run a computation that was highly proprietary on that column. So the next step is, how do you build the invocation grid? So this gives you an illustration of how you might build an invocation grid. And we don't need to look at the details, but the thing that's interesting here is, first of all, that you specify the classes and the dependencies, and then you instruct the grid to load this into the grid and associate it with a namespace. And so what the grid does is, the first thing it does is it reads the code itself and stores it as an object in the grid, and then it multicasts a startup to all of the grid servers, which then spawn say, JVMs on every grid node or grid host. And then these JVMs read in the code as data, which causes one to consider the implications of that from a security point of view. And then they're ready to run method invocations for Java-based data structures which reside in the grid. So that's how that works. And the nice thing is, unlike the standard Apache MapReduce, these invocation grids can persist as long as you want. So the startup time can be handled once, and then you run invocations all day, all night, until such time as you want to re-up the invocation grid. So the nice thing about this, now we've built an extensible mechanism for running methods of data structures that are hosted in the grid, and they're run outside the worker process. So they're secure, their language, arbitrary languages can be used, they can access distributed data structures within the grid. And so now we're getting parallel speed up. In fact, it's this term embarrassingly parallel. And this was coined by a guy who worked at Intel at the time I was there. His name is Cleve Moeller. You might have heard his name. He was a creator of MATLAB. And he came to Intel. He was also the author of the LinPack package, linear equations package, with Jack Dongarra from Oak Ridge. And he was a well-known mathematician. And he ran into this problem of, how do you get parallelism in the grid, and how do you get speed up? And he recognized that if you can do a lot of independent things in a grid, now you have what's called embarrassingly parallel speed up, because all of these things can run independently and add computing to the grid. So notice there are two types of speed up you're getting here. One is you can handle multiple requests from a single client and also multiple independent clients. So in fact, Grid's pretty good for handling streaming requests. Believe it or not, it's really a good streaming engine, because these method invocations can be used to capture events from an external system and apply them to objects in the grid. And likewise, multiple clients can do that at the same time. Now, the pros and cons of doing this, I think we've talked about this, and I don't want to take up too much more time on this topic, but it is secure. It allows you to run arbitrary languages. And the problem that we face here that's really you can't avoid is that you have to pass objects across the process boundary here. And as I mentioned, there are ways to mitigate that, but that problem still exists. Furthermore, the grid implementation itself has to do the orchestration to move the code, to do code shipping, and to bring up the IG workers. And there's a lot more under the floor that we didn't talk about. In particular, there's heart beating between the grid service and the IG worker, and you have to have mechanisms for globally shutting down grid workers and checking their status and handling the failure of one grid worker. There's a lot of stuff that goes on. But the bottom line is it's a very powerful mechanism. So let's talk about the next step is, OK, now we can run methods on individual objects in the grid, wouldn't it be nice to have a data structure that spans multiple servers in the grid, a huge data structure? And something that comes to mind is like, how would you implement a climate simulation? How would you implement MapReduce even? You know, how do you do operations which are data parallel? Now, one of the things that I learned many years ago, the power of data parallelism is it's really simple. You have a single method that operates on many, many data structures in the grid. And compare that to task parallel, task pipelines like Storm, and I'm not knocking Storm, but it's a task parallelism is a more complex programming model, especially for application developers who understand their data structures, they understand their domain-specific operations on those data structures, but they're not particularly interested in orchestrating parallelism to get speed up. They prefer that somebody else worry about that. It's just how can you avoid complexity in the application, and data parallel programming avoids complexity in the beginning, and that's its main value. It also allows a grid to achieve parallel speed up. So you can think of data parallelism as running a method on an object in the grid, but then doing that same invocation on many, many such objects spread across the namespace of the grid. And also, typically, you would want to combine the results of a data parallel operation. So back when we first did this in Intel, there was an API called MPI, a message passing interface, and the standard data parallel, or the term people used back then was domain decomposition. The standard technique was broadcast an operation, run it across a domain, and combine and retrieve all the results. And it turns out you can easily build MapReduce as two phases of that. I talked about that last year, and we have information about that. But that's just sort of an interesting aside. That MapReduce can be built as two phases of broadcast merge. So this is what happens, is the client invokes this operation, this eval, which then gets sent to all the grid workers in parallel using multicast, software multicast I'm speaking of. And then it runs on a whole set of objects in each grid host, which have been selected to run this operation. And then once all the results are computed, you can optionally merge those results, and then you can globally merge across the servers and return one result back to the client. So that's what data parallelism can give you, this ability to really scale what the grid is doing and get more value out of in-memory computing. So this is, again, a way it could be implemented the way we do it in our product called parallel method invocation. And again, we're leveraging the object-oriented view of data. So objects within a collection are instances of a type, and you can define two methods. One we'll call an eval method, wherever it is up here, and another called a merge method. And so the eval method, notice, can take a parameter, unlike a mapper, by the way. Very interesting. That a eval method can take a parameter object, which can have many parameters in it, and then can return a result. And the merge method can combine results. We implemented binary merging here so we could build a binary combining tree and very efficiently return results back to the client. And you can see at the bottom what that invocation would look like. And I'm going to give you an example in just a minute. In fact, right now. So here's an example in financial services. This is a real customer we have. So it's a hedge fund, and they have stocks that are in portfolios. So they have a big collection in the grid. Their namespace is a collection of portfolios, or they also call them strategies, in different sectors like high-tech, real estate, automotive, whatever. And so in each portfolio, they have long positions and short positions. And the goal of a hedge fund is to keep a balance in the value of those so that they minimize risk. So what they want to be able to do is, as the market prices change during a trading day, they want to evaluate all those portfolios to see if they need to make a trade to rebalance one of those portfolios. That's a perfect data parallel operation. Now you have a large amount of data that can be executed in parallel, that can be analyzed in parallel, based on one method that's run in parallel and uses as a parameter a market snapshot. So this is the UI we created for them. And so what it does is it runs a parallel method invocation once a second based on the last 1 second's market snapshot. And that gets multicast out as a parameter. So all they're called strategies here, are analyzed in parallel. And then the merge comes back to the UI. We were able to demonstrate about 350 milliseconds to do, I think it was 2,000 strategies. By the way, we have a YouTube video of this comparing it to Apache MapReduce. And that was taking about 15 seconds to do the same thing. So in-memory computing really does speed things up. And so what happens is the merge tells us which portfolios to highlight here, and then when the user clicks on that portfolio, then the user can see this is just the contents of the object, and you can see the long and the short positions and where the imbalance is arising. So that's just an example of data parallel computing in the grid using an object-oriented view of data. This is the actual code for doing that. So this is a portfolio object. Notice it has long positions and short positions, and it also has other parameters or properties which can be queried. And then it has this very interesting method. This is a method that knows how to analyze it based on a market snapshot. And one of the interesting aspects of this that is not related to performance or data motion is the fact that the separation of concerns. Because by implementing with this object-oriented view, the hedge fund can keep all of its highly proprietary evaluation code in a nice little method. Notice this whole thing, other than these attributes, has nothing to do with an in-memory data grid. It can be run as a for loop. In fact, they were running out of a SQL database before this. And so the separation of concerns makes it extremely valuable to the customer because you don't ever have to see their proprietary code. And so this is how you connect the methods that you're going to run. This is the method that we just talked about to the grid itself, this implementation of an interface, which I will skip for today, but I can discuss it with you. And then with one program statement here, you invoke the full data parallel operation and get a result back here. So all of that orchestration of the execution of the eval and the merge and all of that stuff is just under the floor of this one operator on a namespace called invoke. And that's the power of data parallel programming. It's very, very simple, and yet it's very powerful. What happens is on each server, I skipped the part that we're actually supplying a query spec too, so that you can confine or filter the number of objects you want to actually operate on based on their properties. So the first thing that happens is the filter takes place, and then the objects that are filtered go into the execution engine where the cores are used to do the eval and the merge. And then the end of that is one result object, which are globally merged with a binary merge tree. So all of that just takes place as part of our grid infrastructure, and it allows the customer to have a very simple view of data parallel programming. I thought I'd add this slide because I never put up this information. This is what I learned from Cleve Muller. Now, Cleve didn't get credit for this because another guy at Los Alamos named John Gustafson, you might have heard of, also a very famous guy, who will tell you why floating point can be dangerous, unrelated. They recognized it about the same time and both published, and John won. But the point is that this is the big insight that occurred in 1985 about clustered computers. In this case, we were calling them parallel supercomputers, but they were just clusters of commodity processors with a special purpose network between them. And that is that you don't want to do what Amdahl's law would tell you to try to do, which is to take a problem of a fixed size and try to make it go faster by throwing it at n servers instead of one server, so that the time it takes to complete is divided by a factor of n. So for a workload size, let's just call it W here. So this is not what you want to do. So if on one server you can do 1 unit of work or W items in time t, in latency of t, you don't want to try to make it go to t divided by n by applying n servers. What happened was Cleve was doing matrix multiplication with a fixed size matrix, and he said, okay, it works great on one server, let's do it on 2, and it got slower. Let's do it on 4, it got even slower yet, right? And that's when he said, okay, I think what we need to do is scale the problem size. So as we add servers, we grow the workload so that on n servers, we get n times the throughput for n times the workload, and that gets done with the same latency. And that sounds like a lot of gobbledygook, but if you think about it, it's intuitively what you expect. So if you have a web farm and you're handling W users, and then you say, well, okay, I'm happy, they get 10 milliseconds response time. So now I've got twice as many users on Mother's Day. I'm a florist, you know, so I get twice as many users. So I want them still to get 10 milliseconds response time. So what do? We have 2 web servers. Now we can handle twice the load, twice the throughput, the same latency. So that's scalable speed up. It's really quite intuitive once you think about it. And that's what we want to accomplish with grids. The problem we run into is the network can kill throughput, as we saw before. Also, hotspots are bad programming or bad implementation of a grid. We spend a lot of time making sure we eliminate any kind of asymmetric hotspots in our grid. And that causes the latency to rise and the throughput to tail off. So this is an example of a measurement we did about 2 years ago. This is laughable now, because last week when I was having somebody review it, they said, you realize you can put a terabyte in one instance in Amazon now. We did this in 75 instances in Amazon, because that's what it took to get 1 terabyte of highly available, that is to mean 2 terabytes of data in the grid, and then run a data parallel operation. This was a stock backtesting operation we ran. And we were able to, what our goal was to see what is the effect of this being live data. We're going to change the stock prices while we're doing the backtesting. So this represents a live system. So for example, this could be, patient monitoring pacemakers, telemetry flowing in, and the objects represent the history of telemetry for a patient, and you want to analyze to make sure that patient's not about to have an event. So what happens if you start throwing changes to the data while you're doing these map-reduce operations on it, the data parallel operations? And what we saw is we get nice, perfectly scalable speed up. This is what we want to see as the problem size gets bigger and the number of servers increases when there are no updates. Now, as soon as you have updates at 2 different rates, then you can see you start to tail off. And we attribute that to network bottlenecks in the infrastructure in Amazon. Of course, it'd be impossible to know exactly where the bottlenecks are. Nevertheless, even with 1.1 gigabytes per second of updates, we're still getting a complete analysis in 4.1 seconds, which, if you think about it, is pretty fast if you had a 1 terabyte drive to basically analyze all the data on that drive in 4 seconds. It's pretty good. So the technique you use to achieve data parallelism is loosely called sharding. And we used to call it domain decomposition, which means you take a data structure and you carve it up into little pieces and operate on the little pieces independently. So Redis has shown us how you can do sharding in a single server, and Lua scripts can take advantage of that. There's an example in the book Redis in Action which does that. And it takes a Redis list and shards it, and then makes it very, very fast to access the list, because now you can have multiple concurrent access to different parts of the list. However, when you start talking about sharding across multiple servers, it gets more interesting. How do you shard a data structure so that you could spread it across a set of servers and then do data parallel operations on it? And so this is an example of something we did, which is the challenge we had. We were implementing about 4 years ago an Apache MapReduce engine to run on in-memory data so that you could run code unchanged on an in-memory data grid, hosting key value pairs either in HDFS or in the grid. And then we realized if we're going to host key value pairs in the grid, there's a gazillion little tiny 100-byte key value pairs in the word count example, for example, that we were trying to do at the time. How do you host this big bag of key value pairs? So that's a big parallel data structure that needs to be sharded. So the approach we took, just as an example, is to chunk the key value pairs. And I also want to mention, we wanted to allow the key value pairs to be accessible individually with Java concurrent map semantics, in addition to being available for MapReduce. So we have 2 different usage models, and we want to have an efficient storage mechanism. So we chunk them into objects that are stored in the grid and put a little hash table in each chunk. So these are the chunks. And then for MapReduce, you just pipeline the key value pairs out of the chunks and use them to define the splits, and for the reducers, the partitions. And so you can read them from the grid, go through the mappers, and shuffle them into another name map, and then do the same for the reduce step. That's what I meant by the 2 phases of the parallel method invocation. And so by doing this, you can get nice parallel speed up for a data parallel operation, and yet have very fast access to individual key value pairs. And the other benefit for that is by hosting these chunks and grid objects, then as you load balance these objects, when you add and remove servers, it naturally load balances this workload across the servers, and you don't have to push that knowledge into the client of how to shard this data structure. In fact, I think it's one of the lessons of the work we've done in grids is really good to have the load balancing and the availability mechanisms inside the grid and not in the client libraries. That's just my personal philosophy, because it simplifies the user's view of the grid instead of forcing the grid libraries to track and implement that and to handle problems like, how do I add a grid server? It also is very efficient. So finally, let's look at combining these into one operation. And this is, again, this is a proof of concept we did for a customer, a cable company. And so their problem was they have 10 million set-top boxes, and they have people watching TV and sending on, off, and channel change events to them. And what they want to do is to capture those events, and they want to correlate them by set-top box. And it was taking them 6 hours because they were storing them on disk and then reading them off disk and correlating by set-top box. Then they have to cleanse out by their proprietary rules which events are interesting. So they can tell if you've fallen asleep on the TV or if you're just channel switching and so forth and so on, have a whole set of rules. And so you want to cleanse them, and now you have events you care about. Then you have to enrich them with what programs are people watching or what program did they switch from to. And then you want to pass that to their internal recommendation engine so they could maybe upsell you with some pay-per-view or an ad or something else. So that's the goal. And they needed to be able to do all of that in under a second because, you know, they don't have much time to get back to you and tell you something before you're off doing something else, right? And also they wanted to look at the aggregate statistics for what is the overall population of cable viewers doing? What are the most popular shows? You know, maybe we should do a special offer. You know, maybe we have network bandwidth problems in a certain area. We talked to a customer in Spain about this, and they said, oh, well, we don't actually have this problem. We have another problem. People start watching soccer matches, and all the network bandwidth gets sucked up, and we don't have a way to shed load by having the low-end customers get poorer quality of service. They needed a distributed mechanism for handling that problem of making sure that they could handle these hotspots in their overall network. So in-memory data grids are really good for this because you can represent the state of a set-top box object as an object in the grid. Let me say that again. You can represent the state of a set-top box as an object in the grid. And as events stream in, you can use that single method invocation we talked about to update the state of that object and keep track of in a list of events. And then you can enrich those events and do all that work with the single method invocation, while at the same time, you can look at the aggregate statistics across all users. Now, I presented this to somebody last week at a very large computer company, and they gave me an example. They said, oh, I get this. I see why this might be valuable. And they gave me another example, which I think I have time to tell you, which I think is quite interesting, which is, you know, with airport security and all of that, you could conceptualize having this kind of technology track people coming into an airport, and with facial recognition and all, you know, what you would do is with a single method invocation, you'd look to see, is this a person of interest? You could look up their history and see where else they've been in the airport and so forth. And then at some point you might say, this is a person of interest. Now you then immediately flip to a data parallel computation where you look at everybody else in the airport and say, okay, who might they know? You know, what events did they do that could correlate with events other people did? You know, so you can imagine all kinds of algorithms that could be employed to try to establish: is there a pattern here? Is it one individual or is there a pattern? So you could see how single method invocation and parallel method invocation, that is to say, data parallel computing and single methods on data structures, can work together to solve a bigger problem. And one of the interesting things, this just as an aside, one of the reasons you want to do this outside of the grid service is you really need the ability for the grid worker to call its own SMIs, to be able to access objects outside of its own local server. This is an example from the cable proof of concept where in order to enrich the event, you might need to call the channel guide, which could be represented as another object, and have an SMI that takes an incoming event that has a timestamp, a date and time, and then give you back what program was being watched, just as an example. We actually did it a different way. This illustrates how you might want to be able to have full access to the grid within the grid worker itself. So this was the UI we gave to this particular customer, and we were able to meet their need of doing this analysis and enrichment every second. You know, we could enrich every event within a second. Handling, their goal was 25,000. We demonstrated 30,000 while computing the top 10 programs by zip code in under 10 seconds. We did this on 10 servers in Amazon. And I see I'm down to 5 minutes, but luckily I'm on my last slide. So recap. So what have we talked about? We talked about in-memory computing, really in its purest sense. How do you, instead of just using a grid as a passive cache and pulling data out into application servers, how do you move computation into the grid? And what can you achieve by doing it in terms of parallel speed up and taking full advantage of the cores and and the systems within a cluster that makes up a grid instead of just using it as a data store. We saw the first step was using baked-in, pre-baked data structures inside of the grid service, and then building extensible data structures in the grid service. And then we saw that you could move that computation into a separate worker process for extensibility to have better extensibility and flexibility at a price of more complexity and inter-process communication overhead. And then we saw how you could apply these techniques to data parallel programming. So now you can, with a very simple program, run a very big computation that hopefully scales linearly on a cluster of servers in the grid. And I think I have one more click. Come on. Oh, here it is. Yes, the bottom line, and it is literally the bottom line, is in-memory data grids are a great platform for in-memory computing. So thank you very much. Let me know if you have any questions. Thank you.